So why did we go through all that trouble to talk about the impulse response of a linear time invariant system? Well, the point is that the impulse response tells us more or less everything there is to know about the linear system. And why is that? Well, the main observation is that any reasonable input signal can be approximated by linear combinations of shifted rectangular pulses. If you remember how the Riemann integral is defined, it's often the case that you take an interval and split it into a bunch of small intervals, and then you approximate the function with or the function graph perhaps with a series of rectangles. And when you want to compute the area under the curve, you can sum the areas of the corresponding rectangles, and as the width of the rectangles go to 0, the value of this approximation gets better and better. And we're going to do something similar here, because any reasonable input signal can be, as I said, approximated by, or the graph can be approximated by rectangles, or if you prefer, the input signal itself can be approximated by a linear combination of rectangular pulses. And since we have a linear time invariant system, we can easily compute the system response to such a linear combination of rectangular pulses. So more precisely, if we write f as an approximate sum of function values or at some chosen points, we can, for example, choose a number of points evenly distributed, spaced delta apart. And then if we multiply these by p delta shifted by the same amount, t minus tau k then, and then we multiply by an extra delta, because if you remember, these p deltas were scaled so that the height of the p delta was 1 over delta. And when we do it like this, we don't want to have that scaling, so we put it back by adding another delta here. And in fact, we really want to write it like that, because we will see in a second that this is more or less the Riemann sum of an integral. So if we now plug this approximated function, approximated input signal, through the linear time invariant system, you will see that you will get a sum of f of tau k, which is now just a constant, and then the system responds to shifted p delta. And since we have a time invariant system, that's just a shifted or time shifted response to p delta. And if you let delta go to 0, this is actually the Riemann sum, or this will looks like a Riemann sum, and it will approximate or even converge to an integral as delta goes to 0. And if we look at this, the terms in this sum a little bit more carefully, we can convince ourselves that it will actually converge to an integral of f tau times h of t minus tau d tau. And with some reasonable assumptions on the linear system, all of these approximately equal and hand-waving convergence can be made precise. I'm not going to tell you exactly what the conditions are, but for systems that show up in practice, all of these will be satisfied. So in fact, the output signal corresponding to the input signal S can be computed from f and the impulse response h by this kind of integral. And this kind of integral is called the convolution of f and h, and sometimes written by an asterisk or a star, f star h. And convolutions have many other applications as well. You will meet convolutions in several disguises during this course, and also during other courses you will take during this program. Summing up here, loosely speaking, if we know the impulse response on a linear time invariant system, we more or less know everything, in the sense that we compute the system response to any reasonable input signal through this convolution or this integral. And of course, to do this for a concrete system, we need to know the impulse response as good as well as possible. And of course, we need to be able to compute that integral. Now, computing the integral is not really an issue, because even if you can't compute it exactly, it's usually not a problem to compute a numerical approximation as good as we want. So a lot of the study of linear time-invariant systems has to do with studying the impulse response of the system, methods to determine the impulse response, and also ways of using the impulse response to say other things about the system. For example, things like stability or long-time behavior of certain input signals. You will find examples of all of these things and much more later during the course.